I would like to discuss with you a modification in the current mirror. Some people call it degradation of the transistor. We would like to call it negative feedback. So we are going to add negative feedback to the mirror, and we are making the mirror, the transistors itself better. So you see, I have a shorter length, only 180 nanometer, 50 micrometers wide. So I'm probably in a much higher inversion level with this transistor, but also at a higher FT. But I add series feedback in the stage, and this of course fixes the gain of the stage, so the GM of the stage of this to R3, and the GM is responsible basically for the noise. So if R3 is much larger than 1 over GM of this stage, as we have seen with local feedback stages, the loop gain in this stage is considerable, and the noise that can be low because I'm working in high injection. It's a low voltage I have to define now by a very low, multiply with very low transconductance, which is set by the resistor. So the current noise of the output stage will be much lower. So the idea is that this is an alternative for making a very long FET that would give me a low FT. Here I can still deal with a high FT and still deal with the noise performance, but now do it in a completely different way. So let's study this one. And this is called dual stage mirror with resistor. So it's a high transconductance PMOS with local feedback. And extra attention, of course, is exactly the same as we did before, the selection of the loop gain reference. If you select it such that it is meaningful. Now let's go to the file. And the file is this one with a resistor. So I will run it to create the output. And you see here, I define the resistor 200 ohms, so which sets basically the transconductance to 5 milliamps per volt. And the first FET was 20 milliamps per volt. So the noise contribution is lower than, it's about 4 times lower than that of the first FET, roughly expected at this point. I also want to select the loop gain reference in the first stage. So here again, you see this parameter that I put to 0 to have a meaningful loop gain. But of course, for the gain later on, you can leave it in, but then you don't look at the loop gain anymore. You just say, okay, this is the gain. And you can later, if we are talking about frequency compensation, optimize your frequency compensation. But you cannot use loop gain pulse product anymore because it's not so meaningful. So let's run this one. Now we have also a nice plot. You see, we have still the same, but if you compare, you see here 2, 3, 4, 5, 6, about 700 megahertz is now the peaking, and it was about 500 megahertz, which means that the frequency is increased. You see where the loop gain now crosses the 0 dB axis is 2, 3, 4, 5, 600 megahertz instead of the 400 megahertz that we had before. So the effect of this feedback and of the other way of dimensioning the FET is definitely there. You see, we have already a higher cutoff frequency. And of course, in this case, we are not simulating the noise. Let's go to the, so what I expect is a much higher FT. Let's go to the HTML output to see some more. Let's click the wrong thing. I'm just overwriting every time the index file and then a new one is created, because you can also put everything in one file, but I didn't do so. So circuit data, what we are expecting now is a higher cutoff frequency, a higher FT for the transistors that are part of the mirror, which is U4 and U3. So let's look at FT again, which is completely down. You get here first, you get all the capitals, and then you get all the U3 and U4, and you see indeed it's now about it's about 10 gigahertz, which is about 10 times more than it was. It was 900 megahertz. It's now, it was about 1 gigahertz. It's now about almost 10 gigahertz. So basically, the effect on the high frequency behavior is exactly what we wanted. The GM, of course, of this stage will be much higher, but this is not representative for the noise anymore because there's feedback in the stage. So that is what you have to take in account later on. So you can look at GM of U3 and U4, but it's only 5 milliamps per volt. It's not that bad. So it's already better than it was. So I selected the better operating point for the FETs. So for the noise, this is definitely beneficial. Um, Then let's go to the pole zero, because we expect now for the pole zero analysis that the gain, you remember the Q was about 3 in the previous one, and it's now 2.2. So the gain has lower Q of the poles, but still frequency compensation is necessary. So you might conclude at this point that from a point or from a viewpoint of frequency compensation, it is probably not a big deal. I think we can compensate both this complex poles and the complex poles in the previous case, because it's either you have a Q of 2.2 or you have a Q of 3, which is not really a big deal. But for the noise, it might be a better solution. So of course, there's a lot to optimize. You can really optimize things here. This is just a first guess. So here are again are the plots, but now a little bit larger. We see indeed where the the loop gain passes through the 0 dB line. That is where we have the bandwidth limitation. That's where you now see the peaking. Maybe it is nice also to show you that the integrator is gone in the loop. This line doesn't go up to 100, 150 dB or so. It will saturate somewhere because, and it will saturate at a few megahertz. We have seen at the first dominant pole because of the output impedance. So the only thing you need to do for that is run your plot again and set the lower frequency to a lower value. So here we do the phase and the dB plot, and we start at 100 megahertz. Let's start at 100 kilohertz and do the same thing. And then probably we will see the effect of the output impedance of this current mirror. It wasn't necessary to do everything again. Yes, I could just have run the plot because it uses the result of the Fourier transform. But now you see here, the loop gain ends at 40 dB. So about 100 times loop gain we have at the best. So that is we can maybe better see it in the HTML file. This HTML file. Reload. And then you have here the 100 dB, the direct, and all the transfers of the asymptotic gain model.